Alrighty, so we'll go ahead and get started. So thank you for joining everybody. For this is going to be a demonstration walkthrough showing how a few different national lab-led efforts around data collection, data standardization, and data processing can all be used together. So we'll start out with a discussion about the MODAQ system, which is a data acquisition system developed at NREL. Then we'll have a demonstration and discussion about the Marine Energy Data Pipeline, which is a standardization code base led by PNNL. And then we'll have a demonstration discussion about MHKiT, which is an effort, a tri-lab effort between NREL, Sandia, and Pacific Northwest National Lab, PNNL. So I'm Rebecca Feo from NREL, and I'll be kind of guiding you through some of this and also then talking about MHKiT at the end. I have with me Casey Nichols from NREL to talk about MODAQ and James McVeigh from PNNL to talk about the ME data pipeline. A few just housekeeping things. We will leave time at the end for questions. I do encourage you to put questions into the chat throughout, and we can answer them in the chat throughout. And then at the very end, we'll get through, we'll answer them and invite you to come off mute, ask any other questions you have, or continue to put them into the chat. So with that, we'll go ahead and get started. So I'll just start by giving just kind of an overview of the MODAQ suite to kick it off, but also just kind of put into context where MODAQ fits in with the ME data pipeline and MHKiT. So MODAQ is the data collection piece, it's the physical hardware typically deployed on a marine energy device, but also can be interconnected to collect data from wave buoys, tidal energy, ADVs, ADCPs, et cetera. We then can funnel the data from what we call MODAQ field, which is that leftmost box, to what we call MODAQ cloud. This is where you have their interconnect then to Portal to start using some of these other tools that we're going to talk about later on. So you can use the ME data pipeline then to standardize your data set. With this, and James will go into elaborate a bit more on what that means, but really kind of clean up your data, do some QC, and then get your data put into a standardized format that enables easy post-processing and analysis. We also then, from that point on, can then easily use MHKiT. MHKiT is the open source data processing software that you can do your post-processing, your analysis, you can produce graphics, et cetera, and I'll talk a little bit more about that later on. We also have a third component of MODAQ, which is MODAQ Web, and this is where we can show data analytics and also show some of the data in near real time coming in off of the MODAQ field hardware. So this is a great tool, and Casey will talk a little bit more about this later on, about how you can use this to look at your data, monitor your data, and make sure that your device is operating nominally, et cetera. With that, I'll pass it over to Casey.
Thanks, Rebecca. Just a quick introduction. Casey Nichols from NREL, and I'm a research engineer here. I work on the MODAQ project, developing the hardware and software for data acquisition for different ocean energy technologies. We'll talk a little bit about the MODAQ system, and I'll start off with kind of the field aspect of it. So I'll start off with the picture. You see, this is kind of our MODAQ field enclosure. This one was deployed or will be deployed with the OE buoy. And the main purpose of the MODAQ field enclosure and system is to acquire the data. Right now we have a lot of modules for different types of sensors. The whole design of MODAQ is modular, where you can configure it to your different needs for different deployments, and including the IEC tests you may want to do in the field. So right now we have modules for the strains, loads, temperatures, voltage measurement, electrical current, acceleration, rotation, GPS, position, analog signals, digital signals, and a bunch of typical things that you would be interested as an ocean energy device developer. And we're adding new ones, all the time. So if there's not a capability that exists now, it's our motive to add those. And then after kind of the raw data collection, there is a lot of capability for analyzing the data within kind of the embedded hardware of MODAQ field. A lot of the analysis will happen in the cloud, but some of it you need to happen at the device, kind of for near real-time monitoring and that kind of stuff. Of course, we have the monitor. There's a lot of capability for kind of HMI control within MODAQ as needed, because a lot of times developers, need to turn things on and off with their device. So we include HMIs that are kind of connected directly to the device. So even in the field, developers can talk to the MODAQ and see what's going on with the device, for field repairs and maintenance and that kind of stuff. And then lastly, we have a control element within MODAQ. It's more on the SCADA side, which is like more supervisory control, but it has kind of expanded into more advanced control, like with PIDs and fuzzy logic, that kind of stuff. So just the main points of this slide is MODAQ is reconfigurable, rugged, and capable, and is being used in several deployments or soon to be deployments that are happening in our marine energy industry. So we can go to the next slide. Thank you. I'm skipping the middle one, which was the MODAQ cloud, and because that's most of the presentation after the MODAQ section with ME data pipeline and MHKiT. But another component is the MODAQ Web. This is the near real-time dashboard for kind of monitoring different deployments. With our deployments we have going on now, each one has their own dashboard, which is accessible by the different developers. So they can anyone from their company can log into this website and see exactly what's happening with their device. So it can display a ton of different things. All the data that's collected in MODAQ can be, processed and put on this website. Because it's traffic lights for conditions and you name it, we could have this included on the MODAQ Web. One thing to note about the kind of stack is that it's containerized and scalable, responsive, secure, and extensible. So we put a lot of work into developing this web component for device deployments, and encourage the use of it for different deployments that are going on. So next slide, please. Okay, talk a little bit about the technical details of the MODAQ hardware. It's built around National Instruments Compact Rio, which is a real-time Linux embedded PC that also includes an FPGA. National Instruments is kind of an industry standard for R&D measurements. Where NREL has historically used their hardware for decades, and it's just it's a great suite that we can rely on. So the Compact Rio runs a Linux operating system, but it's kind of National Instruments' own flavor of Linux, where they actually abstract a lot of the most complicated parts of programming real-time systems and FPGAs. So we can leverage the capability of that kind of really complex data acquisition features and LabVIEW, which is kind of a graphical programming language that is maybe a little more accessible to non-computer science background individuals. So a few important aspects of MODAQ to highlight is the GPS nanosecond precision timekeeping. This allows for, all of our sensors to be time-stamped to the correct time so you can compare them with all sorts of other remote systems that are also synchronized and allow for a more distributed data acquisition system. There's also high-speed GPS corrected motion tracking, or INS. And this is kind of a filter between IMU data and GPS data that actually greatly improves the position tracking of your wave device, which we all know is really important for floating devices in the ocean. Also, MODAQ includes the ability to connect to it remotely. So that's kind of crucial when we're seeing, or we need to debug things going on with the wave energy converter. We need to be able to connect to that MODAQ system, even if it's in the middle of the ocean or, you know, on the shore and wets or pack wave, all those places. And then lastly, we have cloud access with that remote connectivity, includes internet connection. So we're able to pipe data right to the cloud, which kind of enables all the second components of this with the web and the cloud. And then, of course, the SCADA functionality, which is definitely necessary for a lot of devices. So I'll just speak to these figures I have. The top right one is kind of the system architecture for a compact Rio, where you can see it has the real-time processor. It's just a regular, or it's an Intel processor, x64, that's connected directly to an FPGA, which kind of allows for streamlined communications between the two. And then all of your I/O modules connect to the FPGA, which enables them to be communicated with at very high speed. So we're able to do like 50 kilohertz sample rates and definitely meet all the requirements for IEC standards, and hopefully with whatever a developer would need. And there's our water power technician, Andrew, building a MODAQ that is deployed in Columbia Power Sea Ray. Next slide, please. Another kind of MODAQ deployment that kind of demonstrated our whole pipeline here was the UNH MODAQ system. It started as UNH kind of had National Instruments equipment and needed assistance with developing it into a fully functional MODAQ system. So we developed modules for them to measure acoustic, Doppler, velocimeters, IMUs, power electronics, turbine drag load cells, and blade strains. So a lot of these modules were developed new for this project. And then we piped all of the data directly to S3 buckets, and James will talk to you how that's processed in the ME data pipeline. We also want to point out that this MODAQ system, being modular, is totally capable of being leveraged for future testing campaigns and IEC accredited testing that may happen on their tidal platform. So next slide, please. This is kind of overview of their tidal platform and kind of the locations of all their sensors. And James will talk about how each of these is kind of processed in the pipeline. But you can see on the bow and stern, we have ADVs that measure the flow into the tidal turbine and out of the tidal turbine. And then there's a lot of the rectifier and inverter, which actually puts power on the New Hampshire grid. We have connection to that, which is measuring the performance of a few of the components there. An IMU, which tracks the position of the platform. Like when a boat goes by, we can see how the wake affects the platform. We have wireless blade strain. We actually mounted 8 full bridge strain gauges on the tidal turbine blade. And because it's a rotating frame, we could not do a wired run. So we had to use wireless communications to get that data into MODAQ. And then the thrust load cells measure, the thrust on the turbine and how it's reacted by the platform. Next slide, please. So we're excited to also be moving to a new kind of system that we're calling MODAQ 2.0. We kind of identified the need for a more open source solution for different MODAQ deployments. A few things to know were the increase to LabVIEW license cost, interest in more options for embedded computers other than the CRIO, where they want to kind of get a better cost, maybe have more scalability, and there's a lot of interest in more energy efficient solutions, so low power computing. Also, a lot of interest in languages that are not LabVIEW, like C++, Python, and Rust. So we actually developed MODAQ 2.0 around the ROS2 architecture for software. ROS2 is the robot operating system, and it's a framework for developing scalable distributed robotics embedded computing applications. But it's actually the perfect kind of architecture for marine energy data acquisition, because it allows for very efficient inter-process communication. It also abstracts a lot of the most complicated parts of building a data acquisition system. So in the development of M2, we hope to make something that's even more publicly accessible and that developers can leverage at any scale. So another benefit of using ROS2 is that it's industry trusted. All the libraries that are included in ROS2 are dependable and vetted. So we want to make that available to MRE developers. And you can see the top right picture is a prototype system. We're still in the early stages of MODAQ 2.0 development, but we have some hardware built and being tested, and will soon be deployed on NREL's HeroWEX system. And the bottom picture is kind of an explanation of how ROS2 streamlines inter-process communication to improve efficiency. So next slide. So that's it for me. I'm gonna pass it over to James. Thank you.
Sweet, thank you, Casey. I, for one, am excited to see that MODAQs can go to ROS2, because it just feels that it makes it more flexible for the whole industry. But to hop into this, good morning all. My name is James McVeigh. I'm an ocean engineer at PNNL, and I'll be giving an overview of Marine Energy Data Pipeline and TIASTAT, how they relate to MODAQ and the UNH project that we're discussing here. I'll also go through a quick run of what the pipeline is actually doing in terms of UNH data as well. So first off, the Marine Energy Data Pipeline is a catch-all term for ME, Marine Energy, related data workflows built with TIASTAT, which is an open source data pipeline that we at PNNL have been developing that can be used to read, process, run quality control, and convert raw data to standard formats. So what is TIASTAT? Why was it created? Well, the main answer is that it seeks to bridge the gap and create a common bridge between experimental data and data that's stored in databases. So it's that cloud block that in the slide that Rebecca showed in the first slide. So for those of you that worked with a range of instruments and DAC systems, it seems like there's not a single one of them that outputs data in the same way. CSV files are pretty common. Sometimes there's a binary format that a company wants you to use their software to decode. There's MATLAB, there's MODAQ, MODAQ's TDMS files, which is a LabVIEW file, and so on. And so you can take the time to write code to organize, quality check it, analyze it, and it gets stored away in a server somewhere, and then you do it again for the next project. And then 2 years down the road, somebody asks you how you got X, and you have to remember what you did and where you saved everything. The idea behind TIASTAT is to build a common code base to assist with that process. So one, to output data in a common standardized format that all researchers can understand. This is kind of the data corollary to ROS2 for those who are familiar with ROS2. Two, reduce the amount of time spent on data wrangling. That's essentially get your file to a point where you can actually analyze it. Three, use a single pipeline framework that's shared across projects, and that's historically documented. So when 2 years down the road, someone asks you what you did, you can point to it, and there's documentation on it. Four, include common quality control tests and data cleaning algorithms. And five, run it either on locally for one-off projects or on the cloud for AWS for real-time projects like UNH we have. Next slide, please. So TIASTAT's approach follows that used by DOE's Atmospheric Radiation Measurement Research Program, which is called ARM. It's part of their wind research. And we built it using Python rather than C++, which is what ARM is built in, to increase that usability and decrease barrier to entry for people. We wanted to include features like storing metadata and quality control with the raw data, and support any size, shape of data, etc., into the TIASTAT platform. It was also important to us to include baseline data standards that we can extend to any domain and keep the code base just flexible and lightweight to be able to handle these things. And finally, make sure key components of the pipeline could be shared across the user base. In this way, if a researcher writes a function or service that is applicable to a particular instrument or system, other users won't have to reinvent the wheel. Next slide. So that's a quick run through of TIASTAT, which brings us to ME data pipelines. These are those pipelines that relate specifically to marine energy projects and carry similar data processing codes, primarily instrument readers, data standards, quality control, and output formats. So for example, any project using MODAQ, there's a reader to pull data from its TDMS files. I'm currently working on a pull request to integrate IOOS standards into TIASTAT. IOOS stands for Integrated Ocean Observing System. It's one of NOAA's programs. Any of NOAA's data you could find online is saved and standardized in this format. Finally, a quality control example would be the Goring-Nikorod spiking algorithm. It's quite common for ME resource data. One of the things I'm actively working on for ME data pipelines is to build up examples from various projects and domains that we have, and releasing those on GitHub page so that people can follow and build their own if need be. My technical specialty is in instrumentation for tidal wave resource characterization, which is what the plots on the right here come from. The top one's from an ADCP, and the bottom two are from a SOFAR spotter buoy. The one is the GPS track, and the other is its vertical motion. So these example pipelines are up on that link on the TIASTAT repo. And I'm currently working on pipeline versions of the MHKiT example notebooks, just to build up more of this domain space and examples. Rebecca will touch on MHKiT after this run. Next slide, please. So this slide shows some example data from the UNH tests. Because I know how to use ADVs, I'm using the ADV here. This is data that has been through the pipeline after it's been sent to the cloud. This is velocity data from the upstream ADV, if I remember right. ADV stands for Acoustic Doppler Velocimeter. It's recorded at 64 Hertz, I believe, so very quick. The plot on the left shows 3D dimensional velocity in the top pane, and the bottom two panes, I know you probably can't read the info on the sides. The plot on the bottom two panes are just acoustic signal quality parameters. The plot on the right shows the in-stream velocity in the top pane, and the bottom pane is an example of a way to visualize the quality control algorithms that TIASTAT is using. It's a pass-fail bar chart, might be the easiest way to explain it. But the y-axis of this bar chart lists each of the quality control tests. There's 7 here from bottom to top. And again, they're hard to read, but essentially this plot marks a red bar for each data point that fails a particular test, and green for those that pass. So each of these tests act independently and on a single point. So you can see if multiple points will fail a test. So if you can see, I guess you can't see my pointer, but there's a very high outlier point on the right side of the top pane. And in the bottom pane, you can see that this fails a number of tests, namely the fail max test. And I believe it fails the despiking test as well. So that was a very quick run through of TIASTAT and the ME pipeline. Next slide, I think, is actually, I'm going to jump into a demo. So I get to share my screen, making sure I can find the right screen. So the first thing I'm going to share, it should be cool. So the first thing I'm going to show is the AWS is Amazon Web Services bucket that UNH is getting stored into. So all this data is coming into a raw folder. It's stored by instrument, each of these folders. I believe it's also stored by year, month, day, which is quite nice for organizing. And then once Amazon gets this data, it runs the pipeline, and all you see is in the process folder is all this data stored. It gives it a name, This is the file format, and stores it in year, month, day. So for all intents and purposes, once the pipeline is set up, it's a black box, which is quite nice, and it resides on the server until someone moves it. So what is actually getting run? I'm gonna pop over. This is the ingest UNH pipeline. It's essentially just a GitHub repo with several folders and etc. The main folders here are the pipelines, the shared folder, and if you're saving it locally, there's also a storage folder. So the pipelines hold all the pipelines for each of these instruments, 1, 2, 3, 4, 5, 6, 7. So for an easy overview of what's in these pipelines and what they're doing, I will jump into the config folder and show the main configuration file. Anything labeled pipeline and TStat is pretty much in charge of everything. So what this pipeline is doing for the load cells here, I say run this particular load cell pipeline. I say trigger it when you see a file. So when Amazon sees a file, it said loadcells.tdms or loadcells.done. I think this is an archive data name for MODAQ. It'll run this pipeline. So the first thing it does is it looks at this retriever configuration file. And this is where the pipeline gets, you tell the pipeline what to read and what data variables to take. So within this file, it's pulling the MODAQ reader, and it's saying, give me these variables from these files that I expect. The next thing that the pipeline runs is everything that's configured in the dataset file. So this is all the standardization. This is where you go in and add all of your metadata, anything specific to the variables that you're working with, so people know what's going on. Once the pipeline standardizes this data, it runs through its quality control tests. These are all specified in the quality control configuration file. Finally, at the very end, we're storing the data. So in this case, I'm using the common storage scheme and then adding this additional, save this as load cells for some extra specificity. That's a quick run through the pipeline. I would hit go, but each of these files takes about 5 minutes to run. So instead, I'm going to pop over here to a demo notebook and simply show you what the raw data looks like and what the final data looks like. So to look at the raw MODAQ data, I'm simply going to pull this custom written MODAQ TDMS reader from the shared folder, the shared readers. This is my raw file that I'm using. I'm going to initiate the reader and run a read command. So this will quite simply show you what is in those TDMS files. And it may take longer because I'm sharing my screen. There we go. So we can see there's 230,000 files. I believe each of these files lasts an hour, so it's quite a fast sampling scheme. There's an index. Time here is saved. I believe that's a nanosecond since 1970. One of the nice things about TStat is it takes those simple data wrangling things like dealing with time when it's in this kind of format and just running it for you, and you don't have to worry about all the different schemes for dealing with time in Python. And then this particular file is from, I believe this is the strain gauges. And so you have, it tells you this is strain, it tells you where this came from in the TDMS file, and it gives you the raw data. One side note, I do like Jupyter Notebooks for reading this data because it's quite interactive. At the end of the pipeline, it's storing it, at the end of the pipeline, it'll store the data as a netcdf file. And so we're using the Xarray package. If you don't know Xarray and you know Python, you should learn the two because Xarray is super useful. What the file looks like after the pipeline is that I have time handled for me. So it's in a legible format that I can read and I know what's going on. 2, I have all the metadata added to the strain gauge variables. So I know these units are actually in microstrain. I know this is strain gauge number 5. I know it's 85 centimeters from the blade root. And it also gives me, I also have my QC variable associated with that. So the QC variables is a lot of where some magic comes in. So this holds all of the test pass fails for this variable. There are 3 points here, flag mask, flag meanings, and flag assessments. So flag mask here has to do with test 1, test 2, test 3, test 4, test 5. Test 0 is if the data is missing. Test 1 is if it's below the minimum. Test 2 is above the max. Test 3 is a valid delta. This is like a change between data points. And then finally, a standard deviations. And this is telling me if any of these fail, that's bad. And so this QC will pretty much mark if any of these fail, it'll be given this bit number. So if test number 3 fails, it's given the value of 4. If multiple tests fail, then it's some addition of these numbers. And I don't know who figured this out, but no matter what way you add these digits together, you will get a unique value. So for instance, if you fail test 1 through 4, then up to 15. If you fail test 5, that's 16. If you fail test 1 and 5, that's 17, and so on. Finally, I just wanted to point out you can save. Since netcdf isn't the most intuitive format for most people, there is a function in MHKiT that you can save this in MATLAB. And we also have tools to save on into CSV as well. With that, that is the full run through for, I think that's what I wanted to go over for the pipeline. It is a bit of a black box, but once it's running, just wanted to show what the data actually looks like. And that I'm going to hand it off to Rebecca, who's going to go over more MHKiT functionality for analysis of these. Stop share.
Thank you, James. Let me get the slide deck back up and running. Okay. So now we're going to talk a little bit about MHKiT. MHKiT's been around for a little while. It was first released back in 2020. So perhaps some of you, hopefully many of you, have used MHKiT in the past. But for those who are not familiar, MHKiT is an open source standardized suite of marine energy data processing functionality. So what MHKiT is really focused on is once you have your data set, being able to do analytics, analysis, visualization, quality control, basically all that post-processing stuff once you have your data set that you would want to do and do some analysis is what would live in MHKiT. We have MHKiT developed in both Python and MATLAB. Originally, back in 2020, our main focus was on codifying the IEC standards. So a lot of our initial functionality has been focused on standard compliant data processing. Since then, we've expanded quite a bit. We've expanded a lot of our data I/O capabilities, so being able to read in different data sets, being able to visualize different data sets. We call those our graphics modules. So different unique ways to look at your data. We do have our quality control capabilities. We've expanded a lot of in our resource characterization capabilities. So a lot of that has to do with the I/O, being able to read in different, ADCP and ADV data, for example. So the absorption of the Dolphin package into MHKiT really expanded our capabilities quite a bit there. Device performance is largely focused on IEC standards, but we've also expanded to looking at things outside of what are prescribed in the IEC. Looking at extreme conditions, capabilities to help you with your device design, for example, and looking at extreme conditions. And then also just all the other unique things that you would want to look at when you're doing your research. We've also, since we initially released, added loads characterization capabilities. I'll be showcasing some of that a little bit later. And then also power quality following the IEC standards. So the big news, we are up to our version 7 of MHKiT. We actually just had a release earlier this month. And the other thing to point out is that MHKiT is hosted on GitHub. And this really makes it a lot easier to access and also enables greater collaboration. So I mentioned we just had a new release, version 7. There's a lot of new great capabilities in this release. If you haven't seen it already, I encourage you to check it out. But two of the biggest things that were added in this release is a new mooring module. So we have a module now that you can use to import data to do some mooring analysis, primarily from Moordyne, which is one of the major mooring models that are used within the industry. You can calculate lay length and then also do some visualization of looking at your line movements in 2D and 3D methodologies. We also have updated our tidal and current resource analysis within Dolphin. So that's including now some turbulence calculation capabilities. And then also we've kind of rounded out the codification of some of the power performance calculations that are prescribed in the IEC tidal power performance technical specification. So looking ahead, we've got some other exciting things that we're going to start working on. We're going to start branching out and looking at things within the acoustics monitoring space, and including an acoustics monitoring module. And then we also are working closely with the MHKDR and the PRIMRE team to develop content for querying content on PRIMRE to kind of streamline and give people other avenues to be able to explore and discover content that's all hosted on the PRIMRE website. That's just a few things. We have other things that we're going to be working on, and we're looking to look closely or work closely with a lot of other projects to help us expand and understand what the needs are within the marine energy industry when it comes to data analysis. So that brings me to, how to contribute to MHKiT. I mentioned that MHKiT is on GitHub, it's open source. And so what really makes that great is that it, beyond just using GitHub to access MHKiT, it also allows for the community to contribute back to it. And there's a few different ways you can do that. So the first would be our issues board. And I always say this, issues don't have to be problems, right? They can be. If you discover any bugs or things that are not working, as expected with an MHKiT, we definitely want to know about it. But we also have these issues boards that are a way that you can provide feedback on what functionality you would like to see in MHKiT. You can communicate where you're having issues when it comes to your data analysis, and we can work out a way to potentially help you. The great thing about these issues boards is, and this is where we like to just kind of go, is that this can be a forum for the marine energy community to discuss, data analysis, what the data analysis needs are. We can work with you then to either get functionality incorporated in MHKiT, or if the issue or the question that you're posing when it comes to your data analysis doesn't make sense for MHKiT, we can help make connections to others within the marine energy community, both in the national lab complex and also outside of national labs, to help make those connections and get everybody doing the data analysis that they need, and start collaborating a bit more when it comes to this. So this is really what we're trying to build with these issues boards. So when you hear issues, don't just think about problems, think about things that you would like to see addressed with your marine energy data analysis. And then the other way that you can contribute to MHKiT is through direct collaboration. What this means is when you have code that you have developed that makes sense to be in an open source forum, and is generalized, that it's not just for your specific research project or for your particular device technology, contribute to MHKiT. I think we've all had this happen to us, where you develop code and then a couple years down the line you've lost your code and you don't know where you have it, and then you have to go and just recreate this code, or somebody in your team moves on to another position and you just don't have the analysis code that they use to analyze a data set. MHKiT is a great place to have your code live, that it can be maintained, and then you can easily access it later on down the line when you need it again. So I strongly encourage you, if you have code floating around on your computers and as you're doing your work, consider contributing that code to MHKiT. And if you're not sure about how to go about this, reach out to us. We're happy to consult with you on what makes sense to live in MHKiT, and we can help you out with getting your code formatted into the appropriate MHKiT formats, etc. So with that, I'm actually going to stop sharing my screen for a minute, and I'm actually going to jump in. I'm going to do a little bit of a demo using the UNH data that we have been talking about here throughout this whole webinar here. So give me a second. I'm going to pull up a Jupyter notebook. Okay. So this is another Jupyter notebook that what I'm going to do is I'm going to walk through using some of that UNH titled data that was collected with MODAQ, then was standardized with the ME data pipeline, and then I'm going to show you how you can do a little bit of analysis using MHKiT. I just want to give a warning in advance. I'm only looking at a very small subset of the data, and the purpose of this demonstration is not to kind of go into any particular findings or do any interpretation on the data specifically. There is a great deal of effort still underway within the project team that collected this data to analyze it, and there are planned publications and presentations around this data set that are in the works. So if you're really curious to find out any kind of unique results from this data set, stay tuned, keep an eye out, those things will be coming. The purpose of this is really just to showcase some of the things you can do with MHKiT, kind of give you a taste of what the possibilities are. Also, of course, this is very tidal energy focused. So for those of you in the crowd that are more focused on wave energy, for example, just keep in mind that this demonstration, you could do similar things with a lot of our wave energy modules that we have in MHKiT. And so just keep that in mind. This is really to show the kind of the ease of how you can analyze your data with MHKiT. So the first things I did are I imported some modules in Python. First and foremost being the MHKiT module, and then a few other packages within Python that are going to be helpful through this demonstration. So the first thing you always want to do is import your data. And so what I've done is I've actually downloaded some of the data from Amazon S3 bucket that James talked about earlier that was standardized using the ME data pipeline. You could do some of this analysis in the cloud. There are ways to do that, but for this demonstration, I downloaded data locally and are doing the analysis on my local machine. So what I did is I downloaded some of the ADV data that was talked about earlier. And so as James mentioned, the data is in a netcdf format. When I imported into into Python, I did import it into an X-array format. At the moment, the majority of MHKiT is required to have your data in a data frame format, so pandas data frames. And so it's very simple, straightforward step to just convert your X-array data into a pandas data frame. And so that's what I've done here. And I just printed out what that data looks like. So for ADV data, it is multidimensional data. So you have your your velocities, your amplitudes, pressures in 3 directions. So we have our X, Y, and Z directions for this data set. And I'll talk in a little bit about how we're gonna convert that data and extract exactly what we need for our analysis. I also have downloaded here some of the strain gauge data. And so basically same step here, imported into X-array and then converted to a data frame. So the next thing that I need to do before we can start diving into our analysis is just really cleaning up the data and getting it into a concise pandas data frame. So what I've doing here now is I'm just extracting. I'm interested in the X and Y direction velocity, from our ADV data. And then I'm also interested in the strain gauge data. So all I'm doing here in this block is converting that data into a consolidated pandas data frame. And then because we have different timestamps between the ADV data and the strain gauge data, I do some interpolation here. There are many methods that you can do to interpolate your data, but it's pretty straightforward to do when you have your data in pandas. So I just did a basic interpolation to just bring our timestamps together and have a consolidated data set here. So now our data is ready to go and we're ready to start doing some analysis. So the first thing you always want to do is apply some QC to your data. So I know James applied QC during the ME data pipeline, but I'm just going to go ahead for the sake of example and do a little bit more. So first step I did is I just wanted to plot really basically here what our velocities are in the X direction. And you can see that we do have some spikes that go up. We actually have some velocities that go up to about 6 meters per second, which for this particular location is not necessarily what we would expect. So what first off I'm going to do is use an MHKiT function called check outlier. And in this function, what you can do is you can set bounds for what you would expect your values of your data set to be. And so I'm just, for this example, I'm setting plus or minus 3 meters per second. For ADV data, negative values is in the ebb direction and positive values are in the flood direction. And so basically what this then outputs is our cleaned data set. And so I'm plotting it again here. You can see now we have, we've cut out all of those outliers and we can move forward with our analysis with confidence that those outliers are not going to skew our results in any way. There's other QC functionality in MHKiT. You can check your timestamps. You can look for corrupt data values. You can look to see if there's any spikes in your data set where, between one value and the next, you have a jump that's unrealistic, in terms of change of value over a period of time. So there's other things you can do in the QC module. So now I'm going to jump into showing some capabilities that we have in our title module on MHKiT. So what we are doing here is we're going to plot our joint probability distribution for different tidal flow speeds and directions. The one thing I will note, if you're familiar with this particular location in New Hampshire, I did not go about correcting for the heading of the placement of the ADV data. The way that they were placed, I believe positive X was in the flood direction and so on and so forth. And so I did not correct. So on this plot, don't get mad at me. The actual directions here, north is not necessarily actually true north, but you get the idea here. If you're doing analysis, you would correct for your heading and so on. But with MHKiT, it makes it pretty straightforward to make this nice plot that'll show how you, that can show your tidal directions, and it'll show your probability of having flow speeds in that direction at a particular speed. And that is with the tidal module. In the graphics submodule, we have a function called plot joint probability distribution. You pass in your flow direction, your speed. We also set your width direction, so you can do different binning for how you want to calculate your probabilities. I did a 1 degree width and a 0.1 degree meters per second speed bins. And so then you can get a nice plot here where it shows how that distribution lies. So next thing we can look at is our a time series of the current in your flow with respect to a particular flood or ebb direction, or really any direction for that matter. And so that's what I've done here. We have a graphics, a function in our graphics module called plot current time series, pass in our direction speed, and I set a flood direction. And you can see here in this time series that we have, you can see the change in direction in our tidal flow going from ebb to flood. And so this is a good way to kind of visualize if you had a longer data set than what I'm looking at here, which is just a few hours, you could see over the course of time, you're changing and you can see your tides, your ebbs and your floods. So the last thing I want to show in the tidal module before I switch gears and show off some things in the loads module is looking at exceedance probability. So this is, we have functionality that can calculate what's the probability that given your data set, it can extrapolate what's the probability that you have a flow, your tidal flow is moving faster than a certain, speed. And so we have a function in our tidal resource module called exceedance probability. All you have to do is pass in your time series of speed, and you get your exceedance probability. And then we also then have a graphics function that can plot this velocity duration curve. And what you get here is your exceedance probability for every tidal speed. And so for this particular case, given that I only passed in a couple hours of data, you can see you get 100% probability that yes, it's moving. But then it goes, your probability decreases as you get higher velocities. Okay, so now I'm going to switch gears a little bit. We're going to look at the strain gauge data that was collected on the tidal turbine. So one of the first things you'd want to do when analyzing that data is you'd want to apply your calibrations. So what we're doing here is we're setting our calibration coefficients and our flapwise offsets for those blades. And these values were determined during the calibration prior to deployment of the actual tidal turbine. So basically we're just setting those values up here. And then we have a function in the loads module called blade moments, where you can pass in your data sets and you can pass in these coefficients and your offsets, and it will calculate your blade moments both in the flapwise and the edgewise direction. For this example, we're just looking at the flapwise direction, so I have the edgewise parameters zeroed out. And we're also just going to focus on strain gauge 3, just for the sake of this example, we're looking at one of the strain gauges. And what your output then is you have your flapwise and edgewise moments. And what I did here is I just plotted it up for that particular strain gauge, what you'd get after you apply your calibration. So after you have your data calibrated, you're going to want to look at some statistics. And so it's pretty straightforward in Python to calculate statistics on a pandas data frame. So what we're doing here in this code block is just calculating your mins, your maxes, your means, your standard deviations for each of the different, all the different strain gauge data, and also we're applying it to the ADV data as well. And then we're going to go about, so I just plotted out the mins here. But then we have a function in the loads module where you can plot those statistics and look at how your blade moments change with tidal speed. And so what we have here is we're using this function plot statistics. We're passing in our mean velocities in the x direction. Then we're also passing in those flapwise moments that we just calculated in the previous section, and then plotting it up. And you can see here then how your means, your mins, your maxes, change with different tidal speeds. So with that, that's the end of my demonstration here. I'm going to quickly switch back to the, I'm going to stop sharing my screen. I'll bring back up the slide deck and we'll take some time to answer some questions. Okay, so this last slide here is really just how to get in contact with us, some links here for more information on MODAQ, the ME data pipeline, MHKiT. And I do just want to acknowledge the University of New Hampshire researchers who obviously contributed to collecting the data that was used during this presentation. With that, let's see if there's any questions. I do see one in the chat from Tony Lewis. The methods used on MHKiT to ensure raw data is error-free and does not have outliers seems to require human intervention, as in your example. Is there any move to automate? Yeah, so you're correct. A lot of the QC functionality does require you to have some knowledge of your data set, right? You need to set, what your expected mins and maxes are, for example. That is an interesting idea to try and automate and come up with ways to kind of auto detect when there's outliers and come up maybe just some statistical analysis on what, your average or standard deviations are. And then if you have any extreme outliers, see if you can flag them. But at this point, we don't have that. I don't know, James, anything in the ME data pipeline in the works to try and automate that process? Or is it, as I said, you do have to kind of set your bounds and what you're checking for?
Outliers in general are hard to, what do you describe as an outlier? Like statistically speaking, it's something that's, outside of the 6 standard deviations. So outside that 99% bounds might be an outlier. The despiking algorithm I mentioned is one of those that uses like a phase state finding function, essentially groups all the points into an ellipse type deal in this phase state space, and anything lying outside this ellipse is considered an outlier. There's a lot of different algorithms in the literature that try to do this. None of them is perfect. The ADV data that Rebecca's looking at is recorded at 64 Hertz, which is at the limit of the instrument. And so there tend to be spikes in ADVs. Looking through that data, it seems that there's other things in the water, just particulates and organic matter that's causing those spikes. But generally speaking, you're going to have to look at your data to know and run some tests on it to know what can be an outlier and what's not. So really, there isn't a catch-all perfect way to do that. I wish there was. It'd make life super easy, but yeah. Maybe the simplest answer is that you can average your data. So like the ADV is going at 64 Hertz. Maybe you can window average that down to 16 Hertz or 8 Hertz, and that'll remove a lot of those outliers. It's quite literally decreasing your standard error in the statistical sense. We won't get into super detail, but hopefully that answers your question. If people have other questions, I think put them in the chat. I'm not sure if the unmute capability is enabled. That's a question for Haley. But yes.
Adam has his hand raised.
Yeah, I have a question. So just kind of thinking in the, if I was a developer who has experience with previous deployments, what are some of the next steps or first steps I could take to, start using MODAQ and the ME data pipeline on my own system?
Well, the MODAQ piece, I don't know, Casey, do you want to take that one?
Well, I think the first step is to take a look at our documentation and identify if the modules we have developed will work for what you need for your deployment. And if not, you can reach out to us and maybe we could help you with that. But the full design is in there. And also you should have some intro into like creating a new module to add to MODAQ. And then, also add that, if you wait long enough, we might have MODAQ 2.0 ready. And that would be, a more open source option if you don't want to go the LabVIEW route. Hope that answers your question.
Yeah, and for the pipeline, the documentation, there are tutorials and there are example pipelines, and that is the easiest way to get started. We do require a basic understanding of how to code in Python. It's a bit critical for setting up these pipelines and really being able to debug what you need to. But there are a lot of tutorials, and the reason I'm working on building up the example pipelines, both from the MHKiT example notebooks, which are also located on the MHKiT GitHub repo. You should check those out if you're looking to learn how to use MHKiT. There'll be similar pipelines, similar example pipelines within the TSStat repo. I definitely recommend those in the tutorials to get started. That's a good question, Adam. Thank you.
Yeah, thank you. It's very exciting to hear about these tools and see them applied.
Okay, I think we have time for maybe one or two more questions. Okay, one in the chat. When do you expect to have 2.0 ready for field testing? Casey, what's our timeline for MODAQ 2.0?
Well, it's kind of being developed in stages, and our first prototype deployment is happening with the HeroWEC deployment, which is happening in the next few months. But it's a very bare bones MODAQ 2.0. But I think it may be possible to have that publicly available within 6 months to a year, at least a basic outline. But full documentation is probably a little further out, maybe a year, 2 years, hard to say. But if you're interested before then, feel free to reach out to me and we can talk about it.
Okay. So not seeing any other questions on the chat or hands popping up. I just want to say thank you everybody for attending today, and don't hesitate to reach out to any of us if you have any follow-on questions, and definitely go check out these links on the page on the screen right now to learn a little bit more and find ways that you can start utilizing these tools. So thank you.